So yesterday we actually carried out the program of Tiltonian RG. For the standard scale of output theory. And we got the following picture. We said there is one fixed point here, and this is what we call the free field fixed point. There's another fixed point somewhere out here, on this guy. So this is the u axis, and this is the m squared axis. Okay? And so basically this guy is the Wilson-Fisher fixed point. And at this fixed point there are, you can imagine that there are basically two different directions. One direction is attractive, and that's the irrelevant direction. And it actually represents just one among an infinite number of irrelevant directions. So this is a section, this thing is a section of the critical surface. And the other direction is the relevant direction. So I thought of a slightly better way of explaining what the critical surface is. So if I take a 2D icing model, and I take just two interactions, right? Let's imagine that the nearest neighbor interaction which I call J1, and I take an interaction with 4 spins, okay, which I call J squared. Okay, so here is J1 in this direction, J squared in that direction. You know that there's a critical point here, right? You are folding in T into J, so J is really J over T, okay? And then somewhere out here, if I just had the square interaction, also I would have a phase transition, okay? And there's some line between them, okay? This line over here is the ordered phase for large J, and there's a disordered phase here. This is an example of a critical surface, okay? Of course, it has a lot more dimensions. Now you can add another dimension here, and another perpendicular to that, and so on and so on. And there'll be some enormous surface. That is what we call the critical surface. Okay? Given your RG scheme, somewhere on that critical surface there will be a fixed point. The fixed point will depend on which RG scheme you use. Okay? And then, however, the direction perpendicular to that, not perpendicular, that's starting with a value thing here, because there's no dot product on these spaces. Okay, but anyway, there's some other direction, there's some linearly independent direction which corresponds to the relevant direction, and the eigenvalue of that, of the fixed point matrix, the linearized fixed point matrix, the eigenvalue of that goes away, that controls the critical exponent here. Okay? And so that was the bottom line of what we talked about yesterday. Okay? Questions? Yeah.
There are two vectors here, right, in the two parameter thing at the point.
Yeah.
So when you're talking about two vectors, you're generating surface, right? So whenever you are changing your control parameter, which is temperature here, say, are you moving away from the surface, or you are keeping yourself on the surface?
Usually you're crossing the surface, because when you change temperature, you change all the parameters. Because remember, the effective action that we're talking about contains an energy and it contains an entropy as well. Right? Because when I force grain my system, right, I look at the energy of that and also the entropy. And the entropy definitely changes with temperature. So all these powers, the phi squared, the phi 4, the phi 6, everything will change as temperature changes. So it's not like, in your phi 4 theory, you're just changing one parameter. When you change the temperature in a real system, you change all parameters. You're moving on some curve through this infinite dimensional space. Now you will cross the critical surface at some temperature along that curve. Now, unless you're extremely unlucky, or unless you fine-tune yourself, you will not be tangent to the critical surface. Okay? Because think about it, there are an infinite number of dimensions, right? And if at all you see a phase transition by changing temperature, that means you have crossed the critical surface. Right? Therefore, I would say it's a measure zero kind of happening if you cross it tangentially. You have to really do something highly fine-tuned to do that. So typically you'll just cross it.
So this relevant direction, I'm actually crossing it like in the sense of the normal kind of way.
No, the relevant direction is some particular direction. Remember, on this page there's no dot product, so there's no concept of normal and parallel. There's no dot product. But there's a concept of linear independence, right? So this relevant direction is linearly independent of the critical surface. It doesn't lie on the critical surface.
That was the question. So this doesn't lie on the critical surface.
It can't, right? Because whatever lies on the critical surface always flows into the fixed point, by definition. That's how I define my critical surface. Right? So it's linearly independent of the critical surface.
So here you have said the infinite number of
Irrelevant direction.
irrelevant. So there is only one relevant direction.
As long as I don't break the symmetry of the model.
Okay.
If I break the symmetry of the model by putting a field, an explicit magnetic field, that's an extra relevant direction. So what I'm talking about here is, while keeping the symmetry of the model, is there spontaneous symmetry.
Basically, if there are, say, capital N parameters, out of which you have drawn two up here, like Euclidean and Euclidean.
Yeah.
That notion of a surface is for n minus one dimensional kind.
That is correct.
Right?
If there's a single relevant direction.
Yes. If there is a single relevant direction.
Correct. That's right.
It comprises of all the directions which are kind of non-relevant.
Correct. The reason is that, again, there's some phase transition, right? There's a region of your Hamiltonian space which is ordered. There's another region which is disordered. And there's a free energy singularity that bounds, that exists between the two. Okay? So what I'm saying is that there has to be, in this situation where it's spontaneous symmetry breaking, there has to be a singularity, a surface, which actually separates your order from your disorder. And that is the critical surface. Okay?
There was one remark yesterday that you made about how you kind of induce this notion of critical surface. Suppose you have the knowledge of these fixed points, right? And you take the evolution very close to that. So you have some directional sense about these fixed points. But from that, this is a local information, right, on the surface. How do you kind of globally translate it? I mean, like, how do you get a knowledge of the full surface in the sense? Because
You don't have knowledge of
I only know it locally, right?
You only know it locally. Yeah, absolutely. So the point is that all you need to know is that it exists, right? And that by changing the temperature in whatever model that you choose to work with, you're crossing it. What's the evidence for that? Evidence is that the model belongs to the symmetry class that you have here, and you have an ordered phase and you have a disordered phase as you change the temperature. That's all it takes. That tells you that you've crossed the critical surface. Okay, and this whole idea is that if you have a fixed point here, every direction except one is irrelevant. Then no matter where and how exactly you cross the critical surface, you will always end up flowing out along this relevant direction. So you will do this. And that is why there is universality. So this explains universality. The existence of a critical point on a critical surface explains universality. Okay? Good?
Yeah, could you, so in the 1D Ising model case, there was only one parameter which, on which you could do RGB and there are 2 fixed points corresponding to temperature string. But here, the relevant direction is sort of a linear combination between m square and u.
Yeah.
So how exactly do you identify, so what is exactly the relation between the relevant direction and the ordered parameter that emerges as a result of spontaneous symmetry breaking? I mean, could you?
Again, it's exactly the same thing. When you actually change the Ising model, suppose there's an exact transformation that you can make that maps the Ising model onto some theory that has phi-4 and phi-6 and phi-8 and all derivatives and everything. There exists such a transformation, and it depends on temperature. So all those parameters that are sitting in your effective action of the continuous field will actually depend on temperature. Okay? So you're sitting in this infinite dimensional space of Hamiltonians, and you're moving along some curve in that space as you change temperature because you're changing only one parameter. You cross the critical surface at some temperature. That is what you would call the critical temperature of the icing. But what I'm saying is it doesn't matter where you cross it. Because as soon as you're sitting at the critical point, you're on the critical surface, you will flow into the fixed point. And now if you're slightly off the critical point, you will flow very fast in here, and then you will start flowing out, and therefore all the long distance universal properties are controlled by this flow, which is the relevant direction. Okay? So it actually doesn't matter which linear combination it is. You see, you guys are very fixated on whether it's exactly this or exactly that, but what you should realize is temperature is appearing everywhere. It's not just appearing in the M square, okay? It's appearing everywhere, in every parameter. All that matters is that you're crossing the critical surface. That's all that matters. And then you are guaranteed universality.
And also the exact location of the fixed point is not really important.
The exact location is not important. That will depend on your RG scheme. Okay? But the exponents are universal. Okay? Good? That's a very important concept.
One more thing.
You had a question.
There may not be a critical point, there may be a limit cycle
Okay.
for the different.
There could be a limit cycle, but in that case, you will not have universality. You see? So limit cycle means what? Limit cycle means that as I rescale, I keep changing and then I somehow come back. So I go through some periodic bunch of rescaled Hamiltonians, I keep coming back, right? To my knowledge, we have never seen a physical system do that.
What about this icing, random field icing one?
What about it?
Probably that has some,
No.
there is some version of it that has some this behavior.
No. No. The only thing that I know about is there is a certain very strange flow in a two-dimensional space in which it goes out like this and it comes back to the same point like this. Okay, this is some version of the random field icing model. I have in fact worked on it myself. But what happens is that it doesn't, so in other words, it goes out of here. Suppose you start at a generic point, it will be somewhere here. This is some disorder axis. So let me call it delta, which is like the average strength of disorder. Okay? And let me call this the deviation from the critical point or something. Okay? And then this will actually go out and then come back into the same critical point. Okay?
Yeah,
But
so is it
these
relevant?
flows are both marginal. So it's not a limit cycle. It doesn't keep going round and round and round. It starts somewhere, it always ends up here. It's not a limit cycle.
So it would have been a limit cycle, it would have avoided that point.
Correct. And come back to itself. Correct? That would be a limit cycle. I'm not aware of any limit cycle. Okay, this is the closest that it comes to what you might call a limit cycle.
What is the system?
Random field icing model in 2 dimensions. Okay? Actually, it's a random bond icing model. Not
Random field.
Random field icing model is a different thing. All right? So what's the motto? The motto is you actually don't care how exactly you're crossing the critical surface. No matter how you cross it, you always end up at the same fixed point, same exponent. Okay? Good?
And
That's universality.
what defines the phase? So just the exponents define the phase?
No, the phase itself is defined by its order. Right?
No, but then what kind of order? There are many kinds of order.
Correct. So it depends on which kind of order you're talking about. So, this is an Ising type order, right? You could have, for example, ON models. You could promote phi from a scalar to something that has some components. And maybe there's some symmetry.
So the symmetries define the phase. What defines a phase?
The order parameter.
Defines
Okay, so the symmetry defines the class of models. The phase is defined by the presence of order or different kinds of order. So for certain order parameters, you can have many different kinds of order. Okay? For example, if you have a spin S magnet, okay, if you had a spin S magnet, for spin a half, you know that S squared is 3/4, right? It's an h bar squared. Right? So there's only one kind of order for a spin a half magnet. It can be magnetic, it can be ferromagnetic or antiferromagnetic. That's it. Okay? But then you could have, if you have a spin 1 magnet, then you could have different kinds of, you could have a quadrupolar order for spin 1 magnets, and so on. So you can have, given a particular symmetry and a representation for that symmetry, you can have different order parameters. And your phase will be classified then by what is the order parameter of that phase. Okay, that's how you characterize the phase.
Then how do you characterize the phase transition?
Well, first you have to know that the phase transition is a second order phase transition. Otherwise, it's just some boring one thing, right? If it's a second order phase transition, then you have a theory of it, which is the Landau-Ginzburg theory. Okay? What is the Landau-Ginzburg theory? You take your order parameter and you write down all possible things that are invariant under the symmetry group of the Hamiltonian. For example, let's take quadrupolar order. Okay, so quadrupolar order corresponds to a symmetric traceless matrix. Okay, so there's a quadrupolar order parameter where the average of the spin is 0 on every side, but the average of this guy is not 0. Right, good. So you ask yourself, what are the kinds of things that I can now build out of this, which are invariants under, let us say, SO3? Because that's the group of the rotation, right? So what can you do? So you can certainly have, the gradient of Q alpha beta dot the gradient of Q beta alpha, right? This guy is the trace of Q squared, and so it's invariant under SO3. You could also, of course, have Q alpha beta, Q beta alpha. You certainly have that. But now you could also have a third order term. You could have Q alpha beta, Q beta gamma, Q gamma delta, gamma alpha. Right? This is allowed by the symmetry of the Hamiltonian. As soon as this is allowed, the generic kind of phase transition that you will have will be first order. So typically quadrupolar phases will under the first order. Okay? If you just had a spin, suppose your order parameter was a spin, not this guy, but just the spin, then you would have to basically characterize it in terms of a unit vector times the size, right? And then it would look like some kind of a nonlinear signal model.
You mean classical spin?
Yeah. I'm talking only about classical phase transition. Okay? I'm not talking about quantum phase transition. Okay, and so on. So you write down your Ginzburg-Landau theory and you ask what it predicts. If it predicts a second order phase transition, then you find out the critical dimension. Typically the critical dimension is 4 for most models. You're working in 3 dimensions, so you have to do your epsilon expansion or something else, and then you find the critical exponents. Okay, so that's how you do it. All right? Okay, so now let's talk about,
I
yeah.
have one question that when we have more than one relevant direction at a certain point, then according to the way we have defined the new critical exponent, there will be 2 different news, right? Corresponding to 2 different relevant directions.
Yeah,
And they will be corresponding to 2 different phase transitions.
no.
2 different order phases.
No, the standard example for so such a point is called a tricritical point. Okay, so you have to tune 2 parameters to be at that transition. So the typical example of that is this liquid gas. So I don't know which way to draw this. Let me draw it this way. Pressure versus temperature. Okay. So let's see. If I'm at very low temperature and very high pressure, I'll be a solid. Right? If I'm at high temperature and I'll be low pressure, that's a gas, right? If I'm at moderate temperature and some pressure, this will be a liquid. I think there's some line. Something like this. Okay, I may have the actual orientation of this wrong, but the topology is correct. Okay, so this guy here will be a liquid. This is a gas. So this is a line of first order transition. That's the boiling transition. Then, so the point is that here, in order to find this point, this end point of the line of first order transitions is actually a second order point. So in order to find this point in a standard liquid gas, you have to tune two parameters, both the temperature and the pressure. Okay? So that's what it means. That's what a tri-critical point is, yes.
So if I tune in some generic direction to linear combination,
You will either find nothing
or
or you will find there's a first order transition. So if I take a generic curve, I'll just do this. Okay? So you have to scan very carefully in order to find this point.
Okay, so let's say I have two relevant directions, and now I fixed one of them.
Yeah.
I find the phase transition. That gives me one set of critical experiments, and one of them
No,
is the new.
usually, so usually, as soon as you move away from a tri-critical point, you either get nothing or you get a first order phase transition.
No, but I am at the critical point. I am to fix.
So you're at the critical point,
At the
right?
critical point.
Yeah.
I fix, let's say, relevant direction 1.
Yeah,
And I'm changing relevant direction 2 to see the second order transition.
correct,
I get a set of critical experiments.
correct,
Now I can do the other way around.
Correct.
I can fix the relevant direction 2 and
Yeah.
change
Yeah.
the relevant direction 1.
correct.
And that should give me a second set of critical exponents. And those two critical exponents are describing
Different. They're
different
different.
type of phase
They're
transitions.
different. They're different. But generically, one of them will dominate. Okay, so the point is that whichever one grows faster, that will dominate. So if you're generically going through that point on some curve, if you have even the slightest overlap with the relevant direction that grows strongly, you will always be dominated by that. So you have to fine tune in order to get the other one.
But the ordered phases are not different anymore, right?
No,
The
order
order
phase
phase are exactly
it will be like this. Yeah. Okay? Good? Alright, so now let's get to the connection with what people do in field theory. How do they do RG? And so the perspective in field theory is totally different. So it's almost exactly the opposite of what we have when we're doing phase transitions. When phase transitions, okay, what we know, we basically know some approximation to the microscopic Hamiltonian. Let me call it energy function. Okay? We know what it is. Okay? We know its symmetry. We know all this. And what we want to know are the critical exponents at the phase transition. Okay? So we know the ordered phases, we know the model, and we want to find out the critical exponents, right? That's what we do in phase transition. Good. And in particle physics,
Sorry?
yeah,
So the initial atmosphere has started with integrating of higher degrees of freedom. How does it fit into this thing? So you were just running temperatures to induce flows.
right. So the point is that, remember, what we know is the mean field level action, right? If you just take that at face value and then you compute the critical exponents, they are wrong because of the Ganpati criteria, right? But we know how to get around that. We know how to do RG. So the critical exponents are obtained by calculating in RG, right? What happens, computing the beta functions, finding the fixed point, finding the relevant direction, all that stuff, right?
Yeah. So how is this RG related to your physical system? Like integrating out higher degrees of freedom.
Yeah.
How is what is the physical picture here? For example, for icing model.
What is the physical, sorry, what?
So you're integrating out degrees of
Right.
higher than degrees of freedom. Why
Right.
does it need to do that?
In which one?
In your condenser system.
Yeah, we do. That's how we find the critical exponent.
So
Okay?
you are saying it is just a tool to find critical exponents?
Right. For condensed matter, it's just a tool
Okay.
to
So
find out what the critical exponents are.
that
Okay?
is really, the physical picture is really relevant for high energy. When you really want to effective action at some low energies, then you are really talking about integrity
That's correct. And the point is that there's some non-trivial flow of couplings in the Hamiltonian, and then you want to find a fixed point, and then you want to find what the relevant direction is, right? So for us, it's a tool to find the critical instance. Good. And we know what the microscopic Hamiltonian is, or we have a pretty good guess of what it is. Okay? In particle physics, it's exactly the opposite. You know some phenomena. You know some low energy phenomena. So for example, you have some particles like the electron and the photon, and at low energy you know how they talk to each other. And you want to construct a microscopic theory of this. Okay? That's what you want. So you want the microscopic theory. Alright, so let's look at it from the perspective of RG. Let's say that there is some microscopic theory that has the same symmetries as your low energy phenomena. Okay? And what would you do? I mean, the simplest thing to do, of course, is to put in the degrees of freedom that are already there at low energies, right? That's what you would normally do. Okay? So you put it in, and then you say, what is the minimal model I can construct? Okay, that has all these things. Now, in general, you could construct many different models. So, for example, supposing I want to construct a theory of electrons and photons, right? What would I do? I would say I have something that looks like this, right? Something like this, A slash, right? Plus F minus, right? I would have this. Okay? This is QED, basically. But I could add lots of things to this. Right? For example, I could add something that looks like, I could add this, okay? I could also add all right? Why don't you add it? Why is it that you don't?
Renormalizability will break down if you add.
Renormalizability is bogus. There's no such thing. What is it? What is renormalizability? What is it? It's just a fact that if you did put it into your microscopic Lagrangian, it would disappear by the time you came down to low energies. It's not a holy principle. It's a result of RG. Okay? Right? This is very important. So renormalizability is taught to you in field theory as though it's a holy principle, your renormalizability. Right? It's not like that at all. It's just that you put in these so-called non-renormalizable interactions at high energies. They're irrelevant. So by the time you come down to low energies, they're gone. Great. You could put them in if you wanted to, but it's useless. Okay? So what you really want is you want some theory that has, there is also an M side or side, right? This guy is renormalizable, so you better keep it. Okay, what does that actually mean? Renormalizable means corresponds to a relevant coupling. That's all it means. Okay, at some fixed point. So, let me write this down. Renormalizable is the same as relevant at the UV fixed point. Okay, so you're trying to guess what is the fixed point at very high energies. That's what's called the UV fixed point. Okay?
So in particle physics, what does mean by this fixed point?
I'll tell you. I'll use an example. Okay? So what it really means is that if you deviate even very slightly from the fixed point, it's going to go away and it's going to actually appear in your low energy Lagrangian. Okay, now of course you're working with Lagrangians because we're working with quantum field theory.
But we always don't know that there should exist a UV fixed point.
We don't know what?
We don't know that whether the theory has a UV fixed point. From the
I'm going to show you that it has to. Okay? That's the assumption underlying this whole idea of renormalizability and so on. You have to have a UV fixed point. Otherwise your whole field theory doesn't make sense. Okay? Why is that? So let's assume that you have it on some lattice scale, right? I'm saying lattice, but it doesn't have to be a lattice. It could be a momentum level. It could be anything. Okay? So this A is basically 1 over lambda. This A is your ultraviolet length. It's a very tiny length. Okay? Now, what I'm saying is that supposing you look at that free field fixed point at the ultraviolet, right? The free field fixed point would be massless, right? It would have just this and that, and nothing else. Okay? And now you say, if I put in a tiny amount of this, it's definitely going to grow, right? Because mass has dimension 1. Right? This guy, if you do the standard dimension counting, the dimension of the fermionic field is 3/2 and 3 + 1, right? Dimension of the gauge field is always 1 in any dimension. Actually, no, that's not true. In dimension 4, it has dimension 1. Okay? It's just that, whatever coupling you put in here, okay, that acquires the dimension. Okay? This has dimension 1, and then the E squared has dimension 0. Right? In 4 dimensions. I'm talking only about 4 dimensions. Okay? The mass has dimension 1. So it's going to grow. Alright? So let's say that's all I want to do. I want to look at the mass. Okay? So what do I have to do at this UV scale in order to get my electronic mass at my laboratory scale? That's the question I should ask. Okay? So mass scales like, mass has dimension 1, right? So what it means is, because it's relevant, the mass at my lab scale, okay? So let me call my lab scale 1 GeV. Okay? It's going to be the mass at this ultraviolet scale times lambda over 1 GeV. Right? Because it has dimension 1. It grows exactly as the scale of lambda over the lab scale. Okay, now if I make my lambda, supposing I want to say that QED is really QED at 1 TeV scale. Right? So what does that mean? So 1 TeV over 1 GeV is a factor of 10 to the 6. So that means that my mass at 1 TeV, whatever mass I have to put into my Lagrangian at 1 TeV, had better be equal to the mass of the electron at 1 GeV, which is nearly the same as the mass of the electron at low energies, divided by 10 to the 6. So the point is, the higher you push the ultraviolet cutoff of your theory, the closer you have to be to the critical point, to the fixed point. Okay? If you want to get the electronic mass at low energies, you have to be extremely, extremely, extremely close to the ultraviolet fixed point. Okay? Otherwise your theory won't make sense. Do you get this idea?
Could you explain once more?
So what I'm saying is that you got some UV fixed point, okay? You got some UV fixed point. Now what you want is the laboratory scale, right? So let me write down a scale, and it's going to go backwards, okay? So let me say that here's my laboratory scale. All right, so let me say this is some momentum scale. All right, it's going to be logarithmic. All right, so here's 1 GeV, and here is let us say 1 TeV, and here is I don't know what else, and somewhere out here is M flat. Okay. So now the question I'm asking is, supposing, and this scale is also logarithmic. Okay, this is my mass. Okay? At the laboratory scale, I have a certain mass. This is the mass of the electron. This is what I want to reproduce. Right? Now I ask myself, supposing my cutoff in my theory is 1 TeV, what mass would I have to put into my Lagrangian at 1 TeV in order to get the electronic mass at 1 GeV? What is the answer to that question? You know that it has to be a factor of 10 to the 6 smaller, because it's a relevant direction. It's growing as you go to lower energies, right? So it has to be very close to 0. Now imagine that I extrapolated all the way to M Planck. It would have to be almost at the critical point. Okay? fixed point. So this is what you're doing in high energy physics. This is what you're doing. You're postulating the existence of a UV fixed point. And you're going, as you increase your cutoff in your theory, you're going closer and closer and closer and closer to that fixed point. And you demand that as I go close to that fixed point, all the correlation functions that I compute depend only on these parameters that are sitting here. And that's the principle you call renormalizability. But it really is just a consequence of RG. Okay? It says that even if you had started anywhere else close to the critical surface, at the end of the day when you flow down to the laboratory scale, you would really have only this guy and that guy. Because those are the only relevant couplings. Okay? Correct? Okay, do you get this idea? Okay, now, unfortunately, QED as it stands doesn't make sense. Okay? Now, you forget all of this and all the infinities that surround any quantum field theory calculation. But as a matter of fact, if I plotted instead of m, if I plotted E squared would actually increase as I went to higher and higher energies. Right? There are a lot of words that go with that. You say vacuum polarization, right? The vacuum polarizes to stream the electron, blah, 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 blah. But the bottom line is that the fixed point, the ultraviolet fixed point is actually at E squared equals infinity. And that's a very bad thing. It's a very bad thing. You don't realize it because in field theory there are infinities all over the place. What's one more? Okay, right? But no, this is actually a really bad infinity because it tells you that your UV fixed point is not perturbative. Okay, the UV fixed point is actually perturbative in this guy. Because as you go to the UV, the mass is decreasing. But it's not perturbative in E squared. So QED is a very badly behaved theory. So it cannot be the theory of everything. Okay, what's wrong with being non-perturbative, you say? Is there anything wrong? No, there's nothing wrong with being non-perturbative, but the method you're using for calculation is perturbative.
No, I don't get it. So,
Suppose I plot the E squared. Okay, so let me plot the E squared. So instead of m, I have E squared. So this ME, this guy, if I plot m of lambda, it will actually go down like this. Okay? Because the m that I want in the Planck scale to get my electronic m is something extremely tiny.
Right.
Good. Now if I plot E squared, the same
bare mass is at high energy.
mass is near the UV fixed point. Yeah.
So what prevents you from postulating a finite but large E square even there? I mean, why do you want to say that if there is a fixed point at some finite level?
Excellent, excellent. Let us assume, so in QED itself, if you just do the field theory calculation, what you find is that this guy actually goes like that. It seems to increase without a problem. You say, okay, maybe this particular thing is wrong, let's do something else. So you go to the lattice. So you go to the lattice QED. And you say, I want to do strong coupling lattice QED. What do you find? You find a confined phase. Okay, you don't find a Coulomb phase. Okay, alright, so I'll reduce the E squared a little bit. Okay? So you reduce it and you do indeed find a Coulomb phase. So in four-dimensional QED, there are two phases. There is a Coulomb phase at low E squared and there is a confining phase at high E squared. But the phase transition between them is first order. So you're dead. There's just no way, there is no fixed point around which you can actually justify ordinary QED.
So sorry,
Did anybody tell you this before? That QED is a sick theory?
So what is the
How many people knew this before I just said this? That's because I told you, okay?
Actually, Nisha told this.
Nisha told you, okay, excellent, excellent. Okay, QED is completely sick. Okay, yeah, now question.
What is the confined phase?
A confined phase. Oh, in a confined phase, electrons don't appear as particles, and the photon is massive. There are monopoles floating around everywhere in a confined phase. Okay? Alright? So QED doesn't make sense. That is why people were so excited when they discovered non-abelian gauge fields. Because you see, if QED is really part of a non-abelian theory, non-abelian theories have this beautiful property called asymptotic freedom. That means that as you go towards the UV, the coupling actually decreases and it becomes perturbative. Okay? The price you pay for that, of course, is that as you go to long distances, it becomes stronger and stronger, and then you have confinement. Right? So you don't have the degrees of freedom that you originally put into your Lagrangian, they don't appear in nature. Right? So that's a drawback, but it's actually way better than QED. The QED is completely safe.
No, actually, that methodology can be an indicator of the new physics coming in between, like the W.
Precisely. Very good. Very excellent. So that brings me to the next point. So whenever this happens, you realize that this cannot be everything. So you know that you need to bring in some extra physics, okay, that will tame this bad behavior in the ultraviolet. Okay, and so it can be an indicator of new physics. But at the same time, it tells you that this program is doomed. This program of trying to observe phenomena in the lab and trying to infer the theory of everything is doomed. Why is it doomed? Because whatever you observe in the lab is always at some finite energy, right? You know that RG forgets, right? You could be anywhere on the critical surface and it would give you the same phenomenon in the lab, right? So you could write down 10 million different theories. They would all have the same prediction. So there is no the microscopic theory.
But that's what we are doing, right? We are trying to go higher in energy, right? Trying to
I'm
see-
saying it's doomed. I'm saying that whole program is doomed. You cannot infer a unique high energy theory. You can infer many of them. They're all equal as far as you're concerned. You sit anywhere on the critical surface, you go slightly off, it gives you the same physics at low temperatures.
Because there are
Just a few relevant parameters. Right. You could mess with the irrelevant ones as much as you want. They would all be different theories of everything. But they will give you the same theory of your energy. Yeah.
Actually, what we are doing is that is the effective field theory kind of thing. That
Correct. So all field theories are actually effective field theories. Okay? So what the best you can do basically is to say, okay, at this energy, this is what the phenomena I know are. Let me write down a field theory of that. Okay? And then if the theory is like QED and it turns out to be sick, then they say, okay, we know that something is wrong, we better fix it somehow. Okay? So you invent a theory of non-abelian gauge fields, you fix it, and then you're happy. Okay? Until some other phenomenon comes along that you can't explain with your theory, right? And then you have to work hard to try to figure out where that's coming from.
so that in the Planck scale that you have mentioned, so some phenomena we can't include in quantum field theory still. So if we can write a field theory up to that Planck scale, so there will not be any infinities coming in.
Well, so I don't know what you mean by infinity. What I'm saying is that if you find a UV fixed point that's perturbative,
Yes.
like QCD for example, it's a very good theory. It has a UV fixed point that's perturbative. It's an excellent theory. It could be a theory of everything. Except, unfortunately, there are things that don't fit inside QED that we also observe, like neutrinos. Okay? So if only there were no neutrinos and no electrons, everything would be great. Okay? Suppose there were no leptons, then we would have a theory of everything. Okay? A very good theory of everything. Alright? Okay? So that is the difference in philosophy between.
But your question becomes a question of precision actually. This thing you are saying with all these directions become irrelevant, the other higher powers.
Yeah.
If you are making a low energy measurement, if you have a very good precision of calculating or calibrating those effects.
I agree. If you could measure everything very precisely, then you would have, you could do better and better.
I mean, the higher power thing that you write, suppose you write some CP odd term kind of a thing, I write a CP event term.
Yeah.
My observable responds to one of them. Then
No, but that's like a more of a digital signature, okay? That's different. You're talking about breaking a symmetry versus not breaking a symmetry. That's very different from adding irrelevant operators that preserve a symmetry.
Yeah. Those irrelevant operators will preserve the symmetry.
Right.
But they may have some kind of, whenever I'll be writing or extending this beyond dimension 4, I'll be targeting some kind of a new physics in mind and like.
But as a field theorist, you will never write something that's actually irrelevant, correct?
Okay.
But I'm saying you could have. You could have without any cost. So your theory, your high energy theory is not unique.
Right.
Okay, but you're right. If I do put in some coefficient at a given scale, let's say I say this is the physics at 50 TeV, and then I measure something at 1 GeV. Of course, a lot of that information has been wiped out, right? But it survives in some very, very tiny amount of irrelevant operator, right? And then in principle, if your precision is sufficient, you can measure it.
It becomes a question.
It becomes a question of precision. That's right. That's right. And of course, the problem is that a lot of these things are strongly coupled field theories at low energy, so you can't compute them precisely.
So that was my question actually, since you have
Yes.
already written this thing. First I was asking that in the way you were starting the Landau-Ginsburg Hamiltonian,
Yeah.
you were writing U6, U8, everything, you can, all those things were already
Yeah.
present in it.
Yeah.
Here suppose you wipe out your other power 6
Yeah.
and power 8 terms, and then you say in your language, if you integrate out those heavy gauge fields or something like that,
Yeah.
they will again come up in your theory.
Absolutely.
So that is how these kind of irrelevant things come up, even starting with a dimension 4 object.
I know.
So
I know.
that was the kind of map I was not
Absolutely.
understanding. So there is a difference, right? You are starting out with everything in place.
Yeah.
Here, even if I start with say dimension 4
I'm
object,
saying it doesn't make any difference if you have all those things.
okay. So it's
That's what I'm saying. If I go sufficiently big scale, if I go to sufficiently big scale, all those irrelevant operators are there.
it's only a difference of dictionary only. Like,
Maybe.
What do you mean by big scale? Big scale in energy?
No, big scale in space. So you start with the lattice model,
Right.
and you go to very long distances, all the irrelevant operators that you could have added, and you might have added, are wiped out.
same thing, no energy.
Okay, so they're gone. Okay?
So what should be the right way of thinking the high energy physics?
This is the right way of thinking. You're sitting near a UV fixed point,
Right.
and if your theory is not sick, the UV fixed point is perturbative.
Right. Yeah.
Okay? Or you maybe there are some certain field theories like supersymmetric field theories where you have non-perturbative control of fixed points which may not be small. Right?
Or you can wait
That's
for-
great. Okay?
Actually, they happily wait for places where they get sick and try to look so whether something is there.
If you want to look for places that they get sick, then there's tons of theories like that. Okay? For example, the Higgs theory is like that. Right? The Higgs theory under quantum fluctuations, all these parameters, right, the m squared, the lambda, all those things, okay, they become sick.
Yeah, the Landau pole we call it.
Exactly. So there are lots of theories which are sick. Okay. So anyway, those are the two different perspectives. Okay. So whenever you do high energy physics, you're assuming the existence of a UV fixed point. Okay. And then if you're very clever, you can find one that's perturbative. All right? So now I could go on and tell you how to calculate exponents using field theory, but I don't think I should, because those who know it already know it, and those who don't know it, I don't think I can tell it in half an hour. Okay? So basically that's the end of the conceptual RT part. And from next week I'll start talking about the XY model.
Yeah, one question is related.
Yeah.
In this RG procedure, always this parameter flow should be monotonic or can non-monotonic have RG as in some?
They could be non-monotonic. For example, there are situations where let me show you a flow that we're going to encounter in the XY model, the 2D XY model. Okay, there's some particular value here. There are two couplings. Okay, let me just call them A and Y, because that's what they're called in the actual 2D XY model. The flows look like this. Okay, they look like that. So this particular part of the flow, this is called the separatrix. Okay? Sorry, not that. This one. Okay, the one that goes to the zero value, which is called the separatrix. And so the point is that here, you can see that as you're flowing, y is decreasing. It decreases for a while and then it increases again and eventually flows off to strong coupling. It doesn't have any motor. Okay? Alright?
That is not a good property. Like, you cannot do this parametrically in this.
You cannot do the what?
Parametrics.
You can do at this
No,
point.
you can do a perturbative
At
thing.
this point, yes.
You're going to do a perturbative thing right around here.
Yeah.
Okay? It's all going to work out. Okay? Yeah.
Will you discuss some exact RG schemes and at least the numeric, some
What do you mean by exact?
numerical RG or something? Please
Numerical
how
RG?
the concept or how they are formulated.
No. I probably won't. In fact, I will certainly not. Because I don't know exactly how they're formed. I know only something schematically. I've never worked on numerical algebra. Okay? So now the choice is that it's going to take about a week to do X, Y, Y. After that, what do? I can just goof off, but Srimati won't let me goof off. So I can do a number of different things. Okay? I could do discrete lattice gauge theories. Okay? We learned a lot in graduate school about continuous symmetry gauge theories, but we don't learn much about discrete gauge theories, like Z2 gauge theory, Z3 gauge theory, that kind of thing. I could do something on that. Or I could do a one-dimensional RG on disordered systems. Okay? There's a certain asymptotically exact RG you can do on one-dimensional disordered quantum chains. Okay, I could do that. I can't do both. Okay? Or I could just goof off. So those are the three possibilities.
Discrete gauge.
Discrete gauge?
Yeah.
Okay. Fine.
So I have one question.
Yeah.
So whatever you have discussed till now is sort of, you know that there is a phase transition occurring and
Yeah.
you sort of validate the critical exponents close to it.
Right.
But in principle you could sort of start with a theory.
Yeah.
There are multiple order parameters. And
Yeah.
in order to see, and how do you exactly see which ones could be, I mean, do you really see the order parameters and plot the, I mean, observe the flow in the order parameter space and see which ones are relevant? Is that how you?
No, the flow doesn't occur in the order parameter space, right? The flow occurs in the space of couplings.
Right. Okay.
So when a certain the order parameter exists when you minimize the free energy for certain values of couplings,
Right.
there's a spontaneous breaking of symmetry, right?
Right.
So there's no flow in order parameter.
No, what I meant is the
Yeah.
the couplings corresponding to those order parameters. I mean,
Yeah.
There could be sort of like delta and other.
So you mean, is there like a competition between two different kinds of order and so on? Yeah, there are. Yeah, there are.
You can in principle apply the same formalism there also to see which ones.
Yeah, so a standard example of this is something like this, that you have two order parameters and you couple them, okay? So you can, for example, supposing you take two models, one of them is an ON model, okay, so let me call this field, let me call it a phi, and there's some components here. And you could have another OM model, which I will call something else, maybe mu or something, okay? And then you could have, for example, a grad phi A dot grad phi A, right? Plus, R A or R1 phi A plus lambda 1 phi A squared. You can have that. And of course you could also have this. Or 2 sin mu plus lambda 2 sin mu squared. So far these models are independent. But now you could add a coupling to them, and this could now be plus or minus. Okay, so I'm assuming that this number is positive, right? So you could add something that looks like sin mu times phi A. This respects all the symmetries of everything. And now you can ask yourself what the phase diagram would look like. Okay? If this guy is positive, then ordering of one of them tends to suppress the ordering of the other one because it will increase the mass of one of them. And so there's a competition. On the other hand, if you use negative, then there will be cooperation, right? They will both want to order at the same time, and so on. So depending on various parameters, now it becomes a little complicated because there are several different parameters. There's R1, R2, and U. So you'll have to draw like a more complicated, maybe a three-dimensional phase diagram. And see, but this has all been worked out in the 70s. Okay? Yes, all this exists. There is a huge literature on phase transitions.
Just one